Hello and welcome to another lecture based on applications of derivatives. Today we shall be discussing about higher order derivative test for maxima and minima. Later we are going to find the applications of maxima and minima to the real world problem. Later we are going to discuss certain problems that would be based on finding out the higher order derivatives in order to find the maxima and minima of the given function. We begin our lecture with the discussion on higher order derivative test for maxima and minima. Now, as we have seen in the previous lecture, that finding the local maxima or local minima by the first derivative test is very time consuming and of course tedious. So we have another method which is known as the higher order derivative test that enables us to find the values of local maxima or local minima more easily and more quickly. So we have a theorem which is known as the higher order derivative test. For this, let f be a differentiable function on an interval I and let C be an interior point on I such that the derivative of function f at point C is equal to double derivative of function at point C, which is equal to the derivative of function f n minus 1 times at point C, which is equal to 0, and fn at C exists and is non-zero, then if n is even and fnc is less than 0, this implies that x equal to C is a point of local maxima, and if n is even and fnc is greater than 0, then x equal to C is a point of local minima, and if x is odd, this implies that x equal to C is neither a point of local maxima nor a point of local minima. Next we are going to discuss the applications of maxima and minima. The differential calculus is a very powerful tool for solving problems that call for minimizing or maximizing a function, and this would be more clear by considering an example of a problem which states that find two positive numbers whose sum is 20 and whose product is as large as possible. Now for this we are going to consider the figure as shown. Now if one of the number be x, then the other number is 20 minus x, and their product is equal to, let's say, fx equal to x into 20 minus x, which is thus equal to 20x minus x square. Now here the domain of f can be restricted to the interval of 0 to 20. Since the function is continuous, the function has an absolute maxima in the interval 0 to 20, which is located either at x equal to 0, x equal to 20, or an interior point where f dash is equal to 0. The derivative f dash x is equal to 20 minus 2x, which is obtained by differentiating this term with respect to x. This can be further rewritten as 2 into 10 minus x, which is equal to 0 only when x is equal to 10. The absolute maxima is therefore one of the three numbers. We have f0 equal to 0, f10 equal to 10 into 20 minus 10, which is equal to 100, and f20 equal to 0. Thus the function, which is x into 20 minus x, which is the product of two numbers, takes on the largest of these, 100, when x is equal to 10. Thus the required numbers are x equal to 10 and the other number is 20 minus x, which is equal to 10. Thus we have seen that the differential calculus is a powerful tool for solving problems that call for minimizing or maximizing a given function. Next we are going to discuss a problem that would be based on finding the points of local maxima and local minima and finding the corresponding maximum and minimum values of the given function. We have a problem which says find all the points of local maxima and local minima and the corresponding maximum and minimum values of the function fx, which is equal to minus 3 by 4 x4 minus 8 into x cube minus 45 by 2 x square plus 105. Now here in this problem we have fx equal to the given function, which is equal to minus 3 by 4 x to power 4 minus 8 x cube minus 45 by 2 x square plus 105. This implies the derivative of this function fx, which is given as f dash x is equal to minus 3x cube minus 24x squared minus 45x, which can be rewritten as minus 3x into x squared plus 8x plus 15. Now we know that for local maximum or local minimum we must have f dash x equal to 0, which implies that minus 3x into x square plus 8x plus 15 is equal to 0. This gives us the values of x as 0, minus 3 and minus 5. Thus x equal to 0, x equal to minus 3 and x equal to minus 5 are the possible points of local maxima or local minima. Next we are going to test the function at each of these points. Now we have f double dash x equal to minus 9x square minus 48x minus 45. Next, for all the given values of x, we are going to find the value of f double dash x. At x equal to 0, we have the value of f double dash x, that is f double dash 0 equal to minus 45, which is less than 0. So at point x equal to 0, we have a point of local maxima, and the value of this local maxima is obtained by substituting the value of x, that is 0, in the given function. We have f0 equal to 105. Thus the local maxima at x equal to 0 is equal to 105. Next we are going to find these values for x equal to minus 3, and here we have f double dash x equal f double dash minus 3, which is equal to minus 9 into minus 3 square minus 48 into minus 3 minus 45. This is equal to 18, which is greater than 0. Therefore we have a local minima at this point, and the value of local minima at this point, that is x equal to minus 3, is obtained by substituting minus 3 in the given function. Thus we have f minus 3 equal to minus 3 by 4 into minus 3 to power 4 minus 8 into minus 3 to power 3 minus 45 by 2 into minus 3 to power 2 plus 105, which is equal to 231 divided by 4. Next we are going to find these values at point x equal to minus 5. The value of f double dash x is equal to f double dash at minus 5, which is equal to minus 9 into minus 5 square minus 48 into minus 5 minus 45, which is equal to minus 30, which is less than 0. Therefore at x equal to minus 5 we have a point of local maxima, and the value of the maxima at this point is obtained as f minus 5 equal to minus 3 by 4 into minus 5 to power 4 minus 8 into minus 5 to power 3 minus 45 by 2 into minus 5 to power 2 plus 105, which is equal to 295 divided by 4. Thus we have found the points of local maxima and local minima and corresponding maximum and minimum values of the given function. With this we conclude another lecture based on applications of derivatives, which was based on the maxima and minima.